by thanking Sumathi and Sayantan and Rob for inviting me to talk at this discussion meeting, and the ICTS for hosting this. It's always wonderful to visit ICTS. Of course, now we're doing it virtually, but nevertheless. Um, yeah, so I'm going to talk about some other topics in condensed matter physics, which will have some overlap with what Subir talked about. So before I get started, I have a question for the audience, which Subir is not allowed to answer. Does anybody recognize the picture on the screen? No? All right. So this is a picture of the Fermi surface of a familiar metal. It's the Fermi surface of copper. So if you have some time with nothing to do someday, I urge you to Google images of Fermi surfaces of various metals. There's all kinds of wonderful surfaces that show up. And condensed matter physicists have been able to image these precise shapes of the Fermi surface with a number of clever techniques over the last several decades. Okay, so the title of today's talk is, so I'll explain the title as we go along, but the perspective of what I'm going to say in today's talk was strongly influenced by a recent collaboration with a postdoc at MIT. His name is Dominic Els. He just left MIT to join Harvard. And part of our work was a collaboration with another postdoc, Ryan Thongren, who was at Harvard at the time and has recently moved to a shared position between Harvard and MIT. So Sumathi again urged us to start elementary, so I'm going to start at the high school level, or perhaps even earlier. So what is a metal, right? So the first, so the entire talk is going to be about metals. So let's make sure we understand what a metal is. So the most basic level, a metal is a state of matter that conducts electricity. Okay, so I'm going to talk about solid metals, solid materials that are metals. And in solids, metallic conduction is entirely due to mobile electrons that are liberated from the individual atoms that form the solid and swim freely through the material. Right? So you have ion cores, which are sitting at some reasonably fixed locations, and the electrons are detached from these ion cores and are mobile throughout the solid. So that's the sort of high school picture of what a metal is, and it's basically correct. Now, for electrons in metals, perhaps one of the most crucial things to know about electrons in metals is that they form a degenerate fluid of fermions. Even room temperature is cold. The room temperature is already much smaller than the degeneracy temperature of these electrons. And so in practice, this means that you have to treat the electronic motion quantum mechanically rather than as a thermal gas, thermal fluid of charges, right? So the ingredients that go into any understanding of the physics of metals in a solid are the following. So we have to think about a degenerate Fermi fluid of electrons, and these electrons are affected by many things. First, there's the periodic potential of the ion cores that they left behind, and these ion cores may form a perfect crystal, or in some cases they may not. And these ion cores will vibrate about whatever equilibrium positions they have. So these are the four known modes of the solid. And then the electrons interact with each other through Coulomb repulsion. So it's electron-electron Coulomb repulsion. And finally, the electrons will see impurities or other defects like dislocations and things of that sort, other defects that exist when the solid forms. So all of these things affect the physics of this degenerate fluid of electrons, and understanding a real metal involves dealing with all of these in some sensible way. So conventional metals are described by a theory that's known as Fermi Liquid theory, and the name of Landau was associated with this theory. So an ordinary metal, for example, copper, it's one of the most important things to know about the theory of an ordinary metal like copper is that the effects of this inter-electron Coulomb repulsion is actually weakened quite a bit due to Pauli exclusion. Okay, so essentially, Pauli exclusion prevents electrons from coming too close to each other, and thereby reduces the amount of scattering that electrons see from other electrons. Right. So that's equivalently, one could think in momentum space, and as I'll discuss in a second, the important electrons in a metal like copper, fill a Fermi C, and low energy excitations only exist in the vicinity of this Fermi C. Now, since the inside of the Fermi C is inert due to Pauli exclusion, you remove a large amount of the phase space that's available for scattering, right? So the Pauli principle dramatically weakens the scattering due to inter-electron repulsion. So the low energy theory of a metal like copper is built in terms of emergent elementary particles, known as quasi-particles, which are just versions of the electrons that make up the microscopic system. And so these low energy quasi-particles or fermions with electric charge E and spin half that fill up a Fermi C in momentum space. And the highest occupied momenta form a Fermi surface, like in copper, and the quasi-particles are long-lived near the Fermi surface. They scatter only weakly off each other and have a well-defined energy momentum relation. Now, an important aspect of every real metal in a crystalline solid is that the shape of the Fermi surface is not a sphere. We don't have, in a crystalline environment, we don't have continuous rotational symmetry. We only have some discrete rotational symmetry. So there's no reason that the energy, that the quasi-particle dispersion has that continuous spatial rotational symmetry. It won't in general. And therefore, when you fill a Fermi surface, this Fermi surface will not be a sphere. Okay, so this is the essence of Landau's Fermi liquid theory, that even though microscopically the electrons interact with each other strongly through Coulomb repulsion, for the low energy theory, you can more or less get away with an approximate model, with an effective model of quasi-particles, which essentially don't scatter strongly off each other. Okay, so this theory is extremely successful in describing a number of metals, and it's the theory that's standardly described in all textbooks. It's most of the discussion in all textbooks. Now, in the last 30 years, in condensed matter physics, we've come across a large number of metals that violate Fermi liquid theory, and in some cases down to extremely low temperatures that are much smaller than the microscopic energy scales that characterize these metals. So there are two prominent examples that I'll mention. I won't really talk about experiments in these lectures, but let me just mention that the most prominent example perhaps is the parent metal of many high temperature superconductors. So most of you have probably seen the phase diagram of the copper-based high temperature superconductors. So this temperature, and this is basically the electron density in the material, this x-axis. So at some point they become superconducting in a region of the temperature density plane. But if you go above the superconducting transition temperature, they are metallic, but this metal is known experimentally to not be something that is described by Landau's Fermi liquid theory. And there are several other metals that people have studied, which are metals which are very close to the onset of magnetism. In fact, metals of the kind that I think Subhi's lecture tomorrow will develop a basic model for. Things that live on a lattice and have the generalization of the Kondo impurity model to a lattice. in some situations, materials that are described by this Kondo lattice model are seen experimentally to strongly violate Fermi liquid theory. So strange metals are a big mystery and a grand challenge in physics. So a basic question that we are struggling with in the field is how to think about metals where the quasi-particle concept has simply broken down. Right? For instance, one question that they may be interested in, and I'm certainly interested in this question, is the nature of a coarse-grained low-energy effective theory. Fermi liquid theory is a low-energy effective theory of a conventional metal. So what's the replacement for a strange non-Fermi liquid metal? Okay, and the advantage of focusing on a low-energy effective theory is that we might hope that such a theory will capture the universal aspects of several classes of strange metals, irrespective of their detailed microscopic origins. In much the same way that Fermi liquid theory describes a wide class of metals, irrespective of their detailed microscopics. Okay. So in these lectures, I'm going to talk about some steps in this towards this direction. So I'm going to discuss some very general, by very general, I mean model independent properties of clean metals. So the emphasis here is on clean. So I'm going to focus on the idealized situation when we completely ignore any impurities that are present in real solids. Okay. Now, it's whether or not these impurities, which in real life are always present, are central to the essential physics of some of these prominent strange metals, it's not a fully settled question, right? And in particular, for things like the electrical resistivity and so on, it's not a fully settled question. But nevertheless, to get as one angle, one way to approach the problem, I'm going to focus on situations in which we completely ignore the disorder, right? It's an idealization, and the goal is to see what we can learn in thinking about models where we just ignore the disorder, right? And see what kinds of non-Fermi liquid phenomena one can possibly describe if we ignore the disorder. Okay. There is some empirical motivation to proceeding this way, but that's more like motivation. And since I'm not really going to talk about experiments here, I won't give you my particular motivations for ignoring the disorder. Right? So rather than solve the full problem, we'll restrict ourselves to clean metals and see how far we can go on very general grounds. Right? So what we'll see is that any low-energy theory of a metal in a clean system obeys some rather severe constraints, which will then have to inform any full theory of such a metal. Okay. So the plan for the two lectures is that in today's lecture, I'm going to focus on symmetries of the metal, and in particular, emergent symmetries that are present at low energies in the theory of such a metal. And I'm going to relate that to this property that Subir mentioned a few times in his talk, and will probably explain from a different perspective from what I'm going to give in the next talk, the property known as Luttinger's theorem, and relate it to this property known as the Hooft anomaly of the emergent symmetry in a metal. Okay, I'll explain all these terms as we go along. And tomorrow's lecture will talk about electrical transport in clean metals and various general constraints and some ways in which a clean metal may show non-Fermi liquid transport. Okay, so let's get started with today's lecture. Let me start by making some very simple general statements about global symmetry in quantum many-body physics or quantum field theory. So we're interested in situations in which there is some UV theory. In condensed matter physics, that will be the theory of electrons moving on the lattice with some interactions. But the statements in this and the next slide are much more general. So we have some UV theory, and this UV theory will have some global symmetry, which will be described by some global symmetry group, G, which will denote GUV. And at low energies, this UV theory will flow under the renormalization group to some IR fixed point, I'll call this the IR theory. And this IR theory will have some other global symmetry group, which I'll denote GIR. And clearly, the UV symmetry group, GUV, must embed through some map into this IR symmetry group, GIR, right? So I'm going to be interested throughout this talk in situations in which this UV global symmetry is not spontaneously broken in the infrared, right? So the entire GUV is preserved by the low energy theory, right? So that means that this GUV must embed as some subgroup of the global IR symmetry group, GIR. Okay. The first comment to make about this is that GIR may be a bigger symmetry group than GUV. So this is the precise statement of what's known as emergent symmetry. So the IR theory may have symmetries, may have a higher symmetry than the UV theory, right? So in that case, we say the IR theory has some emergent symmetry, a symmetry of the IR fixed point that's not present in the microscopic UV system that this theory emerged from, right? So this is a familiar phenomenon, lots of examples in lots of different contexts. Now, another phenomenon is that this emergent symmetry group, the IR symmetry group, GIR, may have a property known as the Hooft anomaly. And this familiar both in kinetic matter physics and in quantum field theory. For instance, the chiral anomaly of massless fermions is an example of the Hooft anomaly. I guess sometimes people call this the axial anomaly. I was never sure whether to call it the axial anomaly or the chiral anomaly, so I'll keep calling it the chiral anomaly. And this Hooft anomaly will be constrained by the UV theory in some way, and that will be important for many properties of the IR theory. Now, the Hooft anomalies are that's known, and we'll discuss some examples of this, or topological properties of how symmetry is realized in a quantum many-body system. So in the sense that there are no, if you add perturbations that deform the same phase of matter, right? These deformations preserve the Hooft anomaly, right? So these are topological in the sense that you can deform the IR fixed point, and so long as the deformation, you can deform the IR theory, for instance, by adding irrelevant perturbations or things of that sort. But so long as you're at the same fixed point, this anomaly is something that is not modified. So it's a topological property of the low energy theory. And this is the reason, one way in which the study of topological phase of matter informs the study of other non-topological phase of matter. So this entire meeting is supposed to be on topology and strong interactions in quantum systems. So my entire talk is going to be about gapless phase of matter, which are not by themselves topological, but nevertheless, there is a way in which topological concepts will play an important role in understanding these gapless phase of matter, and that's the one way through which it will impact this talk, or through these Hooft anomalies. Okay, so let me describe the systems I'm interested in. I'm going to be interested in UV systems with a global internal U1 symmetry and lattice translational symmetries that live on a d-dimensional lattice. So in kinetic matter physics, this global U1 symmetry will simply correspond to electrical charge conservation. So we can think about electrons hopping on a lattice, right? That in a manner that conserves the electron's charge. And this will define the UV global symmetry of my system, right? So throughout the talk, I'll not specify the Hamiltonian of the system. So I want to talk about model independent properties. And the only thing that I require is that the Hamiltonian is local. That is, it is the sum of operators that each act on local regions of space. Okay, so this is a very, very general setting, and it includes almost all models of interest and standard discussions of strongly interacting electrons. People have probably heard of the Hubbard model and various variants, the Kondo lattice model that Subir briefly mentioned at the end of his talk, and we'll discuss in more detail tomorrow, and many other things, right? It will not include another model that has been studied quite a bit in the last few years. It's the Sachdev J. Kitaev model, which is a model with random interactions. So that model does not have lattice translation symmetry. Okay, but it includes, that's why the statement here, it includes almost all models of interest. So it'll include things like the Hubbard model. Okay. So I'm going to be interested in quantum matter, meaning phase of matter, that are compressible. So let me define this concept of compressibility. So let N be, which we'll interpret as the electric charge, be the generator of the global U1 symmetry, and let mu be the corresponding chemical potential. So then we can define a thermodynamic susceptibility, which is the derivative of the average value of N with respect to mu. Okay, and this susceptibility is what is called the compressibility in condensed matter physics. So I'll be interested in phase of matter where kappa is non-zero. So within such a phase of matter, typically we can tune the density continuously without changing which phase we are in. The classic example is a free Fermi gas at a non-zero density. The standard example, and that you probably know from basic stat mech. Now, the non-Fermi liquid metals that we eventually wish to understand, the evidence in experiments is that they're all compressible. So there's good reason to focus on compressible phase of matter. So next, I want to define the concept of lattice filling. Given these UV symmetries, global U1 and lattice translational symmetry, we can define the lattice filling nu as the average charge per unit cell. Right? We take the total electrical charge, the total global U1 quantum number in the system. Let's take, for instance, in 2 dimensions, let's take the system with L by L number of sites and take L very large. And we take the total amount of charge, the total particle number in the system, divide by the total number of unit cells, and take the limit when L goes to infinity. Okay, so that defines the lattice filling nu. And the statement of compressibility is the statement that in a compressible phase, we can tune mu continuously without changing the phase of matter. Okay, so that's the specification of the UV theory of the class of UV systems that we are interested in. So now let me turn to the IR system, right? So the first thing we want to understand is how lattice translation embeds into the IR theory. Now, if we think about a unit lattice translation in the UV theory, now the IR theory is obtained by coarse-graining the lattice to obtain some sort of continuum theory at low energies. And in this coarse-grained version, elementary lattice translation by one unit appears as an infinitesimal translation in the IR theory. Okay, so this suggests that a unit lattice translation in the UV theory is simply an infinitesimal translation in the IR theory. And this is more or less right, but it's not entirely right. That's why there's a tilde in this sentence. More precisely, we should allow for an action by an internal symmetry of the IR theory. In other words, a unit lattice translation of the UV theory embeds into the IR continuum theory, not just as an infinitesimal translation, but a combination of an infinitesimal translation and action by an internal symmetry of the IR theory. To illustrate this, let me take a simple example. Let's consider an antiferromagnet, an Ising antiferromagnet on a lattice. You can think about a classical Ising antiferromagnet on a two-dimensional square lattice. And we imagine we tune the system to its critical point, right? So this will have a finite temperature of phase transition, and we tune it to its critical point. And the IR theory of this critical point is, we know that that's described by continuum 5 to the 4 theory, where this phi field physically describes the antiferromagnetic order parameter, describes long wavelength fluctuations of the difference of the magnetization between the two sublattices of the square lattice. Okay, so the continuum IR theory is the standard 5 to the 4 quantum field theory. Now, lattice translations take me from one site to the neighboring site. Under these lattice translations in the IR theory, these lattice translations act, of course, as infinitesimal translations, but they also have the effect of flipping the Ising order parameter, the antiferromagnetic order parameter. And so, in addition to infinitesimal translations, the lattice translations embed as a discrete internal Z2 symmetry that flips phi to minus phi. Okay, so this is the usual story. So the usual story then is that lattice translations embed into the IR continuum theory not just as infinitesimal translations, but a combination of infinitesimal translations and some internal symmetry. Now, there is some subtlety to this usual statement, which happens if the IR theory doesn't actually have a continuum limit. It's not a continuum field theory, and if there's no spatial coarse graining, but this is sort of it's a very subtle thing, and I'm not even sure it can ever happen in a system with a finite number of degrees of freedom per lattice per unit cell. So I'm not going to worry about the subtlety at all. And but we should keep this in mind for the future if this entire story that I'm going to tell you is somehow runs into some serious problems. Okay, so next I want to talk about constraints from the UV on the IR theory, right? So this is the kind of constraint that we're going to explore in great depth. So let me start with a very simple example, hopefully familiar example. Suppose the IR theory is fully gapped and is smoothly connected to the most familiar kind of insulator in condensed matter physics, a band insulator. Now, it's a standard story in condensed matter physics that this can happen only if the lattice filling is such that nu is an even integer. Okay, it's basically because then you completely fill a set of bands. You have the possibility of completely filling a set of bands, and it's nu should be even because you have two spin species. There's up spin electrons and down spin electrons. So this is a very general statement. If you know that the IR theory is fully gapped and smoothly connected to a band insulator, you know that this can only, such a low energy theory can only arise from a UV system which has lattice filling where nu is an even integer. And I want to emphasize that this familiar statement is actually a really interesting statement because it's Hamiltonian independent. It's a completely model independent statement. It's just a very general statement about when you can get a band insulator. Okay. So there's a more famous, I won't say more famous, a less famous, but more subtle example of a very similar constraint from the UV on the IR theory. And that's this Luttinger's theorem, which both Subir and I keep mentioning in our talks. So this is a theorem about Fermi liquids. And the statement about Fermi liquids, the statement of Luttinger's theorem is that the volume of the Fermi surface is completely fixed by the electron filling. And the way it's fixed is that 2 times the volume of the Fermi surface divided by 2 pi to the d. In other words, this is the volume of the Fermi surface in units of the size of the first Billow zone is equal to this lattice filling nu modulo an integer. Okay, So this statement is an obvious statement if you have free electrons. In the free Fermi gas, the volume of the Fermi sea is just set by the density, even in the presence of bands and so on. But it's also true in Fermi liquid theory for strongly interacting electrons, so long as the ground state is a Fermi liquid. And this is proved to all orders in perturbation theory by Luttinger, using the kinds of things that Subir discussed in his talk, the existence of Luttinger word functional and things of that sort. Very interesting and beautiful non-perturbative argument for the same statement was given much later by Masaki Yoshikawa, about 20 years back. And the thing that I want to emphasize once again is that Luttinger's theorem is a Hamiltonian independent statement. It doesn't care about what the Hamiltonian is, so long as the ground state is a Fermi liquid. Okay? So the next few slides, what I'm going to do is to revisit Luttinger's theorem from a modern point of view. Okay? I'm going to cast Luttinger's theorem as a statement about the emergent symmetry and the property that I've mentioned, known as the Hooft anomaly of the low energy Fermi liquid theory. And the advantage of recasting Luttinger's theorem this way is that it will allow us to generalize Luttinger's theorem to more general compressible phases, including non-Fermi liquid metals, right? And these kinds of constraints are extremely important precisely because they are model independent, right? So any dynamical theory that we develop had better satisfy these sorts of general theorems. So this is something that we certainly should understand in our quest to understand non-Fermi liquid metals, okay? All right, so let me start with some very simple example, which is hopefully involves concepts familiar to the entire audience, irrespective of your background, whether it's in condensed matter physics or in QCD or quantum field theory. So I want to talk about compressible matter in one spatial dimension and illustrate how the emergent symmetry and the Hooft anomaly conspire to enable, to give you Luttinger's theorem in one dimension, in one space dimension. So I want to think about, start by thinking about free fermions at non-zero density in one dimension, okay? So these will form, they'll have some dispersion. If you have a lattice, the dispersion will not be just p squared over 2m. But if you have a lattice, if you don't have a lattice, you can just think about the p squared over 2m dispersion. And because they're non-zero density, they'll fill a Fermi C, and the chemical potential will be the Fermi energy. And low energy excitations will live near each of the two Fermi points. Okay. Now, if you linearize the dispersion near the low energy Fermi points, near the Fermi points, you'll find that the IR theory is simply that of a massless Dirac fermion. Okay, that's Dirac-like dispersion in the vicinity of each of the Fermi points. So the global symmetry of the system is U1 cross U1, because in this massless Dirac fermion theory, there's the right-moving fermions, which are conserved, whose number is conserved, and the left-moving fermions, whose number is also conserved. So these two conservation laws together give you two global U1 symmetries. Now, if you just think about the theory of the massless Dirac fermion, and you don't want to think about its origins from the full Fermi C, a massless Dirac fermion, just as quantum field theory, in 1 + 1 dimensions, there's two conserved global U1s. There's the ordinary global charge, and there's the axial charge, which are both conserved. And that's the two global U1s. Now, if you add interactions on top of these free fermions to the system, it's known that interactions are a marginal perturbation in the infrared, and they lead to a fixed line. And condensed matter physics, the resulting fixed line is what's known as a Luttinger liquid. But if you're not familiar with that, that's not important. And this throughout this fixed line, this global U1 cross U1 symmetry is preserved. Okay. So this Luttinger liquid state preserves this global U1 cross U1 symmetry, which is physically associated with separate conservation of right and left moving fermions. Now, so that's the theory. So we can ask about how the microscopic symmetries embed into the low energy theory. Now, the total electrical charge is very simple. It's simply the sum of the left moving charge and the right moving charge. So Q the total charge is n left plus n right. And the other symmetry, microscopic symmetry, the other UV symmetry is the total momentum. And here for simplicity, let me assume continuous translation symmetry in the UV. It's not an essential simplification. So then the generator is the total momentum. And in the low energy theory, the total momentum is simply the Fermi momentum times the difference of the number of right movers and the number of left movers, right? So these equations tell you how the left-hand sides describe the microscopic symmetry generators. The right-hand side describe how they are embedded into the symmetry generators of the low energy theory, okay? Now, the chiral anomaly, so the low energy IR global symmetry has this chiral anomaly, famously for the massless Dirac fermion. So this global U1 cross U1 is broken by external gauge fields. So for instance, if we turn on an electric field that couples the total charge, the left moving and right moving continuity equations no longer separately hold, and rather they are violated by terms that are proportional to the electric charge. In the original microscopic context, this is very simple to understand. If you turn on an electric field in this direction, there's a flow of electrons, along the spatial direction, which leads to flow motion, depletion of right moving charge, and which is then deposited at the right Fermi point. Right, so the entire Fermi sea displaces to the right. So in any case, whichever way you understand it, this is the chiral anomaly of the familiar chiral anomaly of a massless fermion in 1+1 dimensions. And this is one of the classic examples of an Hooft anomaly. So this is the kind of thing that we use repeatedly. And we'll see that this chiral anomaly immediately implies Luttinger's theorem. So let's see how that works, right? So in the original UV theory, if we turn on an electric field, we know what happens to the momentum. It's given by Newton's law. So dp dt, the total momentum, is equal to the total charge, total particle number, I'm interchanging n and q, but the total charge times the external electric field. So this is a very simple equation, very familiar. Now let's try and reproduce this when we restrict to the low energy effective theory and focus on the low energy corner of the Hilbert space. So in the IR theory, from the momentum embeds as kf times n right minus nl. But from the anomaly, we know exactly how n right minus nl changes in an external electric field. So we go back to this previous equation and integrate this over all space to get the rate of change of n left and n right in the presence of an electric field. Okay, and that then gives us the equation that the rate of change of momentum calculated in the IR theory is kf times the electric field times the length of the system divided by pi. So comparing these two equations gives us a relationship between kf and n, which is precisely Luttinger's theorem. Right? So kf is pi n over L, which you recognize as precisely the relationship that's satisfied by the free Fermi gas. But we've now understood this in a manner which generalizes to the interacting system, to the interacting Luttinger liquid, and relates it directly to the property of the emergent symmetry and the anomaly of the emergent symmetry. Okay. All right. So that's the warm-up. Next, I want to talk about 2D Landau Fermi liquids from the same perspective. I want to ask the same questions that we just discussed for the 1D Fermi fluid, right? How do the microscopic charge conservation and translation symmetries embed into the low energy theory? What are the emergent symmetries of the low energy theory? And what is the anomaly of that low energy theory? And what are the consequences of that anomaly? Okay. So the Landau Fermi liquid, and I'm going to talk about 2 dimensions specifically. So UV symmetry is global U1 for particle number conservation times lattice translations, which form a z-squared symmetry group. Z is the discrete group of lattice translations in, say, the x direction. So since we have both x and y, this is z-squared symmetry. And the IR theory, in Fermi liquid theory, is Fermi liquid theory, which, as I discussed, as sharp quasi-particles near a sharply defined Fermi surface. So there's a famous IR Hamiltonian for Fermi liquid theory that Landau wrote down. So the Hamiltonian simply says that there's a one particle energy associated with, so Nk is the quasi-particle number at point K of the Fermi surface. There's a one particle energy, and there's some two particle forward interactions which don't scatter the quasi-particles. These are what's known as forward scattering interactions, but they merely change their energies in the presence of other quasi-particles. So this is the Hamiltonian that Landau wrote down for the Fermi liquid. Okay, so the crucial point is that it's expressed in terms of Nks, which are the quasi-particle numbers that associated with each point K of the Fermi surface. Okay, so let's ask about the emergent symmetry of the Fermi liquid. Now, colloquially, one is tempted to say that quasi-particles are separately conserved for each Fermi surface point, much like in one space dimension, electrons are separately conserved for each of the two Fermi points. And this is indeed true. For instance, if you go back to this equation, the Hamiltonian seems to conserve Nk. The number Nk is conserved by this Hamiltonian, right? It doesn't. There's no scattering that changes Nk in the Hamiltonian. But it's important to be a bit more precise about the statement, which is qualitatively correct. What we really have is that for each point on the Fermi surface, there's a conserved charge density n theta, such that n theta d theta is the number of quasi-particles between theta and theta plus d theta, right? And n theta d theta is the conserved number, while n theta itself is the number of quasi-particles per unit Fermi surface segment. Okay, so the general IR symmetry element should actually be identified with objects like the following. So what generates an IR symmetry, right? It's generated by n theta, but what we really should do is to think about functions like this, e to the I times integral d theta f of theta times n theta, where f of theta are smooth functions that depend on the angle theta around the Fermi surface. So this is an element of the low energy symmetry group. And if you're a bit more formally minded, then perhaps it's not relevant for most of the people listening to this talk. Let me just mention this anyway. The symmetry group defined by symmetry elements like these is the symmetry group of smooth maps from the circle parameterized by theta to the group U1 described by these functions, right? So such smooth maps form a group known as the loop group in the math literature, and we'll just use the terminology, just a shorthand notation, we'll just call it LU1. So this is what we'll identify as the IR symmetry group of the Fermi liquid. The internal the emergent internal symmetry of the Fermi liquid will identify with GIR, with this loop group. So let's now ask how to embed the microscopic symmetries into this emergent symmetry group. Clearly, the total charge is simply the integral of these n thetas around the Fermi surface. This is the total quasi-particle number. Okay. So this is an easy statement. Now, unit microscopic translations on the lattice along, say, the x or y directions, they embed in the following way. So there's a Fermi momentum kf alpha for the component of the Fermi momentum along direction alpha. And the Fermi momentum itself is a function of angle around the Fermi surface. So unit lattice translations along the x at the alpha direction embed as this group element e to the minus I integral d theta kf alpha and theta. So what this does is to change the phase of the electron at each point of the Fermi surface by an amount that depends on kf alpha, right? Now that's exactly what we expect for unit translations if you think about a free Fermi gas and ask how translations act on the electrons that live near the Fermi surface. And here I'm setting all lattice constants to be equal to 1. So we see that both U1 and lattice translations of the UV theory map to elements of this emergent IR symmetry, which is this loop group symmetry, this LU1 symmetry. In fact, it's useful to take the action of translations of the low energy theory as our definition of the Fermi momentum in the IR theory. There's one point of view which is powerful for some applications. Okay. Again, following the discussion in 1D, I want to ask about the anomaly of this emergent symmetry. And first, let me describe this physically. Okay. So in 1D, we saw that the emergent U1 cross U1 symmetry was anomalous in the sense that if I turn on external electromagnetic field, the separate conservation of right and left movers was no longer was violated by the external electromagnetic field. And the same phenomenon is true in the two-dimensional Fermi liquid as well. If we turn on an external electric field, the entire Fermi surface will displace in the direction of the electric field. So you have a conversion of electrons from some Fermi surface points into other Fermi surface points. So the separate conservation of n theta is destroyed, only the total charge is conserved. Now, because we're in two dimensions, we can do something else other than apply an electric field, and that's will also be fruitful. We can turn on a uniform magnetic field and ask what happens. And we all know what happens. There's a Lorentz force on the electron. And so for free electrons, what happens is that the electron will rotate, its momentum will start moving around the Fermi surface. So the electron moves around the Fermi surface, right? Now, this clearly also means that even in a magnetic field, the number of electrons at each point of the Fermi surface is not separately conserved, rather because an electron from here can go there, right? Which it couldn't in the absence of the magnetic field. So clearly, there's an anomaly. This huge emergent symmetry of the Fermi liquid has an anomaly in the presence of an external electromagnetic field. So we want to take this very simple observation, just the Lorentz force, and convert that into a fully quantum treatment. Okay, now it's a very useful physical picture. So I'll describe the physical picture first, and then I'll write down a formal manifestation of this physical picture. So the Fermi surface is the boundary of the rigidly occupied Fermi sea, right? So the inside of the Fermi surface is inert, as I explained, due to Pauli exclusion. You can't scatter electrons into it. So the interior is just rigid. And all the action really happens at the boundary, right? Now in a magnetic field, the interior of the Fermi sea will continue to be rigid because there's no place for those electrons to go. But the electron at the boundary in momentum space, the Fermi surface, this moves around, and it moves around chirally. It moves around just in one direction, right? So the interior is rigid, but at the boundary, there is a chiral edge state, an edge state that just moves in one direction. So this should remind you of a very famous phenomenon in condensed matter physics, namely the integer quantum Hall effect, where you have a sample of a material that shows this integer quantum Hall effect is basically dead in the bulk. It's inert in the bulk, but it has some life at the edge, where there's an electron that's moving around chirally. Here, it seems like we have an analog of this, but in momentum space, right? And in fact, one can show this very precisely, that in the presence of a magnetic field, we can think of the interior of the Fermi sea as showing an integer quantum Hall state in momentum space. And naturally, the boundary, which is the Fermi surface, hosts an edge state that is chiral. It just moves in one direction. Okay, this is just a very simple point of view on this familiar fact from the previous slide of the semi-classical motion of electrons due to Lorentz force in a magnetic field in a Fermi liquid. So the formal manifestation of this anomaly is the following. Suppose I turn on a 2 pi flux of the external magnetic field, so AX and AY. For the chiral K-space edge at the Fermi surface, these n thetas are no longer conserved in the presence of this magnetic field for this physical reason that the particle moves around the Fermi surface, but rather these n thetas now satisfy an algebra that is actually familiar from the edge state of the integer quantum Hall effect. These n thetas stop commuting with each other, right? And the commutator is just a C number. It's proportional to the derivative of the delta function of this angular variable theta minus theta prime. Okay. So I've motivated this discussion through these physical pictures. I'm not really going to prove this equation here, but hopefully the motivation is sort of, the physical arguments are clear. And if you know something about the quantum Hall effect, then you'll understand why this equation is a natural equation. So on with this, let me now derive Luttinger's theorem, okay, in a Fermi liquid. So let's start with the UV theory and ask about what happens in the presence of 2 pi flux. Now, in the absence of 2 pi flux, discrete unit lattice translations commute with each other in the microscopic theory, right? But in the presence of a magnetic flux, these discrete translations no longer commute. And there's a heuristic, simple physical way of thinking about it. If I have an average lattice filling of nu, and I have to turn on 2 pi flux on this lattice, one way in which I can think about it is to take the flux. Imagine I move the entire lattice by around a loop that include, I take instead of moving the charge from one lattice side to the other, let me keep the average charge, let me keep the charge fixed and move the flux through one plaquette, take it from here to there, here, do a circuit like this. And when this 2 pi flux moves around an average charge of mu, it picks up an Orno-Bohm phase of 2 pi times nu. So naturally, the Tx and Ty, these translations do not commute, and the lack of their commutation is precisely given by the lattice filling e to the 2 pi I nu. Okay, so we want to reproduce this equation using the embedding of the symmetries into the IR theory. So if we know that translations embed as this object, right, e to the minus I times the integral of d theta times the Fermi momentum times n theta. And we know the commutation algebra of these n thetas in the presence of this 2 pi magnetic flux. It's this anomalous commutator. So then there's some simple algebra that you can do to evaluate Tx dy, Tx inverse, dy inverse using these two equations. And you get, on the right-hand side, you get something that depends on the volume of the Fermi surface and the lattice constants. So matching these two things, you see that the volume of the Fermi surface gets related to the lattice filling nu modulo factors of modulo some integers. And that matching is in fact precisely Luttinger's theorem. Okay. So this then gives us a derivation of Luttinger's theorem, a non-perturbative derivation of Luttinger's theorem that relates it to the emergent symmetry and the anomaly of the Fermi liquid. And this is a point of view that is something that we can go ahead and generalize to other systems. Okay. So I want to make one brief comment before I finish. I think, again, like Subir, I've gone a lot slower than I expected to, but that's okay. So apart from Luttinger's theorem, several universal properties of the Fermi liquid follow just from knowing its emergent symmetry and its anomaly. Several, but not all universal properties, right? So a subsection of the universal properties of Fermi liquid follow just from its emergent symmetry and anomaly. There's a response to the uniform electric field, which is perhaps not surprising. The electromagnetic response, after all, is dictated by the entire rigid shift of the Fermi sea, and that's related to the anomaly. Quantum oscillations like the de Haas-Van effect, which involve quantizing the motion of the electrons in a uniform magnetic field, are also related to the anomaly. And these properties are related just to the emergent symmetry and the anomaly, what may be called kinematic properties of the Fermi liquid, and they must be distinguished from other universal but dynamical properties. that require detailed knowledge of the Hamiltonian. For instance, require knowledge of the Fermi velocity or these Landau interactions and so on and so forth. But the point is that these kinematic universal properties are almost topological in nature. They rely very general on emergent symmetries and this topological property known as the Hooft anomaly. Okay, I'm going to skip these advanced comments. And in fact, that this may be a good place for me to stop. I think the time is also right. It's just 2 minutes left. So I'll take questions. Actually, I should have said I would have taken questions at any point during the talk. Yeah, Shubhru.
Hi, Senthil. So you have talked about this Yuan charge conservation, but there are other global internal symmetries like, say, spin SU2. So can one think about similar arguments for these other internal symmetries like SU2 and think about putting a gauge field for that symmetry and find out similar constraints?
Yeah, so one can do things, and yeah, one can definitely do things of that sort. Now, of course, the concept of lattice filling is only pertinent to something with the global U1 symmetry. But certainly, I mean, the first generalization you could ask for is what about spinful electrons? And I think that I said really depends on whether the electrons are spinless or spinful.
Yeah.
And it's easy enough to generalize to spinful electrons. You can also, I think you were asking about situations in which you have a system of spinful fermions coupled to a U1 gauge field.
Yes.
You can generalize these kinds of this logic to that system as well. And indeed, we've explored all of that in the paper that we wrote on this topic.
Okay, thanks.
Are there any other questions? Yeah, Anirvan.
Yeah, sorry, the question must be maybe very naive, but in the two-dimensional case, you said the emergent symmetry, you can realize it in the form of this mobility edge where the theta, you said that there is a symmetry which you call this LU1, and that was the emergent symmetry in the 2D case, right? But in the one-dimensional case, when you talked about, you said in the IR theory, the symmetries are already one for the normal particle number conservation, and the other is for the axial charge. And where I couldn't connect actually. I mean, what is the?
Oh, yeah, okay,
emergence?
good. So let me try to make that connection. The story in 1D and 2D is somewhat similar. The 2D is just a bit more subtle. So in 1D, microscopically, we have these fermions at non-zero density, right, which form Fermi points. So the U1 cross U1 symmetry is simply the conservation of particles at each of the two Fermi points. Okay. Now, in the low energy theory, when we linearize near each of the two Fermi points, you get a massless Dirac fermion, and the U1 cross U1 is related to the U1 cross U1 of the massless Dirac fermion in the following way. So this n left and n right, their sum is the ordinary charge conservation, and n right minus n left is the axial charge conservation of the massless Dirac fermion. But it's nicer to just work with the n left and n right basis for many purposes. So what we really have is separate conservation. In the absence of external electromagnetic fields in 1D, you have separate conservation of particles at each Fermi point. Okay, now let's go to the two-dimensional case. In the two-dimensional case, what you have is separate conservation of quasi-particles associated with each point of the Fermi surface. So it's really the same kind of idea in 1D and 2D. Now, the difference is that in one dimension, the two Fermi points, are discretely, they're not connected to each other, right? There's the right Fermi point and the left Fermi point. They're not part of the same manifold, right? They're just discrete points. In two dimensions, the Fermi surface is a single connected object, right? It's a one-dimensional manifold. And so you have to be a bit more careful in defining what you mean by quasi-particle number at each point of the Fermi surface. What you can define as quasi-particle density per unit line segment of this one-dimensional manifold. Okay, does that make sense?
Yeah. I missed that point, at least for the case that these 2 points are kind of disconnected in the 1D, which you connect through this parameter theta in the two-dimensional Fermi surface.
Yeah, in the two-dimensional case, the Fermi surface is a one-dimensional manifold.
Yeah.
In the one-dimensional case, the Fermi surface is zero-dimensional, right? It's just a set of points.
Thank you.
And hence necessarily discrete.
There seems to be some statement made on the chat.
Oh, I don't see the chat window. Let me.
It says, I couldn't understand it, so maybe if you can.
Schwartz P surface. I only understand the word surface. I'm not sure what Schwartz or P refers to.
Okay.
Victor, could you speak up?
Okay, perhaps they're no longer there. Is there any further question? If not, maybe we should thank both the speakers for giving an excellent introductory lectures.